Hi, in this video, we want to look at regression again. Here, we're going to look at polynomial regression, and we're going to look at LASSO regression. Polynomial regression is where we start adding in some higher order terms. When I talk about higher order, I'm talking about squaring, cubing, that kind of stuff. When I talk about LASSO, LASSO is the idea that I don't want to overfit my model. So there's always a difference between our sample and the population that we're trying to understand, get insight into. And if I let the statistical models just run free, I expose myself to the risk of overfitting. Overfitting is where we make our model that precisely fits the sample, but it's fitting the sample when what we want is the population. There's always a difference. So overfitting means that we're letting a model fit too well to the sample when that's not what we really want. In statistics, we never truly know what's going on. And that's why we use data. If I knew what was going on, I wouldn't be doing statistics. I have my sample data, and I'm trying to understand the population that the sample data came from. And so what LASSO does, LASSO prevents coefficients in my regression models from getting too big, and it forces them to squeeze them down. Why do we like this? Well, if I let the coefficients just run free and I have a lot of predictors, what can happen is that I can have two correlated variables. So let's think about it this way. It might be if they're super, super correlated, if this one gets too big and this one becomes a negative value, to like counteract how over big this is, combined, they fit the sample very, very well. But when I go over to the population, that correction aspect drops out. And so I don't want to have that correction feature. So that correction feature is where one variable and another variable or multiple variables get like one of them gets like too big, one or multiple get too big, and then other variables subtract off that too bigness in my regression model, and this will make it look like I have a really good model fitting to my sample. But I don't want to fit to my sample, I want to fit to the population. So what statisticians and machine learning computer science people have done is they've come up with methods to prevent this like incorrect overfitting correction aspect from happening. Okay, so we've been talking about linear regression, and linear regression is a regression model where all of my predictors can be represented on a matrix. All right, so if I have a predictor variable and I square everything in the predictor variable, I can make a new column on my data frame. And I could also take the predictor variable and I could cube it. And then I could take the cube and put that as a new column on my data frame. And then I could take that predictor variable and I could take the square root. And I could take that and put that square root column onto my data frame. I can keep on doing this. All right, so whenever I can put all my predictor variables, whether it's squared, cubed root, reciprocal, anything like that, anytime I can do that, it's called linear regression because I can represent my data as like a matrix format. And so linear regression is not technically linear. Remember, linear is y equals mx plus b or something, plain like that. And we always have an exponent of 1. That's not the case when we say linear regression. So there's a little bit of difference between statistics linear and college algebra linear. Now, something we always want to watch out for is overfitting. So overfitting is when it looks too good to be true. Honestly, when you make a real prediction model, you'll never know if you overfit the model until it's too late. And so you'll always hear overfitting, overfitting, overfitting. That's where we get scared. That's where we get worried, because overfitting means that down the road, I get a jack-in-the-box surprise that, hey, those great predictions you made were complete crap, and now I have to explain that to my boss why the model failed. Bad position to be in. I was in at one time. Just got to deal with it. It's anytime you make predictions, you run the risk of of making bad predictions. And so you always want to make sure that you can stand behind your model. Otherwise, you might have to explain your position, and that's not a fun place to be. For me, when it happened professionally, what happened was that there was a shift in, there were changes in the population. So I had like previous year data, and I was trying to predict like end of year results. And so I used previous year data, and things changed during the time in between. And so there was no way for me to build a model that would be correct. But that's not what my boss wants to hear. And I got in a bad position. I'm all right, but you don't want to be there. All right, so what we're going to do, we're going to take a look at the Boston housing data set. Okay, this data set is a classic data set. This is in like every machine learning program on the planet. Tons of journals like to use this for machine learning stuff. It's a classic regression problem data set. So let's go ahead and start getting some packages. Let's go ahead and get Seaborn and Matplotlib. Get NumPy and Pandas. And let's get data sets from sklearn. And all right, so we're going to have Boston. And for Boston, we're going to have Y is going to be the price. And then all the other variables are going to be our predictor variables. All right, so here are the features that we've got. We've got crime, I think zone, industrial, room, age, tax, PT ratio, B, I don't know what that is, and LSTAT. All right, here's a description of the data set. So here, the stuff that's most important to us are these features of like crime per capita, proportion of residential land zones for lots over blah, blah, blah. So the description of the predictor variables lets us know what's going on. That gives us insight to what we have. We don't have any missing value, missing attribute value, so that's good. All right, so let's go ahead and look at our target variable. Oops. Forgot to do it all at one time. There we go. So here's a histogram. All right, so here in the thousands, we can see that this is the most common. Here's the median, and so it's going to be a little bit less than the mean, because this is going to pull the mean to the right. But so it looks like there's some houses that are on the higher end. So if this was a more typical distribution, we would expect more of a tail here. This would taper off, and all of these values would kind of like drag out. So that shows me we might have a situation where values larger than 50 were just declared 50. That sometimes happens. Or it might be at a certain point, nobody's going to pay for over 50. We don't know. We'll have to figure it out. All right, so let's go ahead and do a visualization to see what's going on. Oops, okay, so this is our linear model. So what we're trying to do, we're taking LSTAT. So if you remember, let's take a look. What was LSTAT? The percent of lower status of the population. Oh, that's wonderful thing to be labeled as. Okay, so we can see a line going through here. All right, so we can definitely see that there is some kind of relationship between LSAT and price. As LSAT goes up, price goes down. Okay, but you notice that there's kind of like a curve here. I see there's a kind of a curve. The straight line doesn't really fit things exactly well. I would like to have a better fit. So let's go ahead and instead, so this is a straight line, correct? Straight line. What if I go with a degree 2 polynomial? What if we go with a quadratic function on this? Let's see what it looks like. Does that fit better? Well, yeah. We can see that over here, I mean, for a lot, as we get farther and farther to the right and farther to the left, we can see that the model is, predicting low, on the far right and far left. And in the middle, it's predicting high. All right, so we really don't want to see a pattern in our errors when we start modeling. If we see a pattern in our errors, we could probably improve our model. Now here, I can see it kind of evens out a lot. I mean, it's still not perfect, but if I don't want to get like crazy complicated, if I want a model that is mathematically compact, this is actually a pretty good representation. Right now we have, this is going to be with a degree 3 model. And we can see that it fits a little bit better, but this seems a little bit wiggly to me. So I personally would stop at degree 2 if I was, if this was my project to present to someone. In general, you want to be cautious about really going above degree 2. There's really few situations where we would go above degree 3. Degree 1 is like the benchmark standard. Degree 2, that's in like special situations. There's situations for, like, let's say things falling from the sky because of acceleration due to gravity. If you remember your calculus, having to go through like, how long will it take for the ball to fall if you throw it up in the air? That problem, that, the solution for that is a degree 2 polynomial. So a situation like that, yeah, that would make sense. I would use a degree 2 polynomial. Degree 3 comes up here and there. It's usually like a cubic splines thing, but most people don't deal with that. If we're going to get that complicated, we're probably going to use a different type of model, honestly. Degree 4, I have never seen a successful degree 4 or above model. I'm not saying they don't exist. I'm not saying I'm not going to possibly use it tomorrow, but I've never seen anything above degree 3 be what I consider a successful model. All right, so let's go ahead and let's do this plot. Okay, so we're gonna plot room versus price versus room. So we can see that the more rooms that a place has, the more expensive it is. All right, now we'll notice that for the very expensive homes, they're really just bucking away from the trend. If I look back up here, they're still kind of deviating out, but they're still kind of in line with the rest. When I look at the room plots, like they're definitely deviating away from what the rest of the trend is. All right, let's go ahead and plot with crime. So we want price versus crime, and we can see that we've got a trend. Now, something that kind of bothers me about this right off the bat is I see that there's a bunch of terms right here, so that's going against. But more so, you see how when it's really close to 0, I've got a bunch close to 0. Now, the moment we get to the right of that 0 mark, we see that the line is above this like clump of points. So something that kind of worries me about this is that I see this as there's actually being like 2 variables on one predictor. I see that there's kind of like 0 and then greater than 0. So something I would consider doing if I wanted to build a predictive model off of this, I would add another predictor variable that has 0 if crime is like 0 or below a certain threshold, and 1 otherwise. And so what that would do, that would modify the intercept based off of the crime, and that I would be able to get better fit for that. All right, let's draw a heat map. Our goal here is to get a better idea of the correlations. So here we're only going to look at specific predictors. So you see I've got indices 0, 2, 4, 5, 6, 12. So these are the ones that look like they're going to be important. Need to do that. There we go. All right, so let's take a look along price, because that's what we're really most interested in. Our colors go from lighter means it's large and positive, dark means it's large and negative. Okay, so I can see that LSTAT is definitely a big one. The industrial is important. Crime is going to be important, age. And room is the only one that is positive from this list. So we can see that price gets pulled down for all the other ones that are that were selected in this index. And we can see that room and LSTAT are the most correlated with price. All right, so here are all the feature names, but what we want to do, we want to take a look at just LSTAT, age, and room, because those look like they're going to be important. And so since they're important, let's go ahead and go with those. All right, so here we've got a scatter matrix. So we've got scatter plots. So what we've got, see if I can get this bigger. All right, we've got room, then we've got age, LSTAT, and we've got price. So along the diagonal, we see a histogram for room, histogram for age, histogram for LSTAT, histogram for price. And now we have a scatter plot for room and age, room and LSTAT, room and price. Here we have a scatter plot for age and LSTAT, age and price, and then LSTAT and price. All right, so what we want to do, I want to just kind of look and see, I've got room, I've got age, and I've got LSTAT. So we can see there's a little bit of curvature here, a little bit of curvature, and that looks pretty straight for room. All right. All right, so what we want to do, we want to build a regression model and we want to make predictions. Okay, when I build models, I need an honest evaluation of how well my model will perform. There are 3 types of sets when I do predictions. Well, actually 4. Excuse me. First one is my training set. This is the data that I use to build the model. The training set we use to build the model. The validation set is a collection of data points that we use to choose among different models. So first thing I do is I train a model. So I take some data, I take a portion of my data, I grab it, and I build my regression model off of that set. Now, I never look at this data ever again. From the data that I have not used, I'm going to take a portion of it, not all of it. I'm going to take it, and what I'm going to do, I'm going to take all of the models that I built, and I'm going to compare their performance on the validation set. So this is my validation set. I compare all my different models, and what I'm going to do, whichever one looks like it's the best model on my validation set, I'm going to pick that one as my winner. So now I'm done with my validation data. I'm never going to look at that again. Next, what I do, the remaining data that I have for model building is what we call the test set. I'm going to take the test set. I'm going to make predictions off the model that I just picked. We make predictions on this data, and I'm going to compare the predictions to what I know to be correct for the actual Y values. And that is my honest estimate on how the model will perform. Now, this estimate is only valid if things between the building of the model and the generation of my upcoming data has not changed. So no matter what, your metrics are always optimistic. Your training data, predictions, the evaluation of the model on training data is always, always, always optimistic. Validation will be somewhat optimistic. Test set will be probably slightly optimistic. Now, the last type of data I have is called the score data. The score data is what in the future I need to make predictions on. This is what my boss actually wants me to do. My boss doesn't care about how I build the model. My boss doesn't care about the validation set. My boss doesn't care about the test set. My boss cares about me giving him a crystal ball to say, this is what's going to happen. That's what he really wants. So the score set is like is when I get all of my predictor variables coming in, I know what the predictor variables are. I need to make a declaration on what the Y value will be. And that's our score set. All right, so in this situation, we're only doing one model. We're doing a regression model, so I'm not going to do any validation. It's just going to be train the model, and I'm going to test it to give myself an estimate on how well it will perform in the future. All right, so I'm going to go ahead and split the data in half into test and train. And that's what the dividing by 2 here does. And you can see these are almost the same size. All right, here is using linear regression. Go ahead and fit it. And so we get our coefficients, and this is using all 13 predictors, which is a lot. Here is our y-intercept. All right, now here we score the model as about 0.86. Now notice that this is on the training set. On the training set, this will automatically be an optimistic value, like no matter what happens. Now, when I go to double check, I took the test set. So when I built the model, I used the training data to build the model. When I did that, the test set was not part of it. It was just kind of off on the sidelines. Now, what I want to do, I want to take the data that the model has never seen. I put that data into there, and I want to go, hey, how well does this fit? If this was my scoring data, would this work out? Would I make good predictions? Well, we can see that this dropped horribly. This went from 0.86 all the way down to negative 2.3. That's a huge, huge drop. All right, well, let's do this again. Let's take a look at the mean squared error. So mean squared error on the train set is 10, and on the test set is over 300. That's a big jump. That's bad. That's really bad. All right, so what's going on? Well, I overfit the model. How many predictors did I have? I had 13. A lot. Linear regression, if I keep on throwing stuff in, it ends up acting, if I keep on throwing in predictor variables and predictor variable and predictor variable, like 13 of them, think of it as like having 13 chefs in a kitchen. Too many chefs ruin the soup, so to speak. Well, yeah, too many predictors ruins the regression model also. I wish I could say that in a more flowing way, but conceptually, that sounded like really cool in my head, that phrase. Too many predictor variables ruin the regression soup. That sounds a little bit better. Okay. So what we want to do now is we want to go through and we want to get rid of some of these. We have 13 variables. Okay. So what's probably happening in this training system is that it's taking the 13 variables, and what's happening is that like one variable is too big, and then the other variables like work with it to subtract off its too bigness. And so the model itself fits very, very snugly to the training data. But I don't want to know about the training data. I want you to know about the population. Okay, so what we did was to simulate the data, the population that I don't know about yet. I used the test set to kind of be as a proxy for the population that I don't know everything about. And I can see that it didn't work out. There's a difference. All right, what LASSO is going to do, it's going to do two things. All right, conceptually, the first one that is the easiest to understand is it's going to find variables and it's going to kick them out. Now, from a regression point of view, it gets kicked out when the coefficient is equal to 0. Okay, so if a coefficient has or if a predictor has a coefficient of 0, it's not in the model. Why is that? Anything times 0 is 0. All right, so LASSO will go through and it'll go, hey, I don't like that predictor. I'm going to kick it out. The other thing it will do is with the remaining variables. So if there is like informative value in a variable, what it will do, it will prevent the coefficients from getting too big. And so I can't have that too big and subtract off to overfit on the training data. So by squeezing it down, this variable never gets too big. So therefore, this one never subtracts off to correct it. Now, if this one still has informative value, what'll happen is it'll have its own coefficient. It'll be just standing out on its own. But if it doesn't have informative value to it after this one's in there, it's just going to have a coefficient of 0, and it gets kicked out. It's out of here. All right, so let's go ahead and do this. Now my alpha is this parameter here, the alpha equal to 0.3. That tells Python like how much room do I want the coefficients to grow, and I can adjust this, make it bigger, make it smaller. If it, I can make it more restrictive or less restrictive with that alpha. If it's more restrictive, my coefficients will in general be smaller, and I will have fewer predictor variables. But what will happen is, in that situation, if it's very restrictive, I might have just one predictor variable or like 2, not very many. If I don't put very much constrictions on the model, what will happen is it'll just give me ordinary least squares or something very, very close to it. My neighbors are shooting fireworks. They just started. I hope they're having a good time. All right, so I went ahead and I fitted a model with LASSO. And here we can see the coefficients. Every time I see a 0, I know that that predictor variable got kicked out. And here is our y-intercept. All right, now what would happen if I change this from 0.3 to 0.9? Let's just do that. Let's do something crazy. See what happens. All right, so previously we had 1, 2, 3, 4 variables kicked out. And here we got 1, 2, 3, 4, 5 variables kicked out. And so I can go through, I can play around with it, try to find the model that I feel the most comfortable. Okay, so let's go ahead and score the model. All right, so it's just below 0.8. Now let's look at our test set. If I score it, ooh, 0.5. That's, compared to -2, that's not too bad. I honestly expected it to be better. That's why I made that face. Let's go ahead and put it back at 0.3. That's what the author did. So let's run it again. All right, so we go from 0.84 to 0.5 about. So let's go with 15. Let's just see what happens. You see, if I set it to 15, it kicks out like a lot of variables. Well, let's take a look at the score. And it stays around 0.5 no matter what I do. All right, so I'm going to go ahead and just leave it as is, because it seems like 0.5 is about the best that this model structure is going to pick up. And here, I only have a few variables in here. 1, 2, 3, 4. I have 4 predictor variables. That means it's going to be relatively easy to interpret, and I don't need to worry about overfitting. So this is probably a pretty good estimate of how this would perform going down the road if I wanted to make predictions on Boston data. We look at mean squared errors. So something that you always want to look at is how much of a jump does your error go from when I go to training set, validation set, test set. If you see a big jump, then you probably have a bad model in there. Which is, and you do this model evaluation pretty late in the process. So it's very discouraging when you see, oh, wow, that thing that I've worked on for 2 weeks gave crap results. Yay. You just got to deal with it. Suck it up. Go back to the drawing board. All right, so Here, we're just taking a look at the maximum and minimums and average of our target variable. So here is the indices for non-selected variables. So these are ones that are not selected. The most important one is number 5. Let's see what happens. All right, so we're saying that room is the most important. And in this system, that's because it's also positive. It's the most important one. And it's organizing them from most negative to most positive on this because there's no absolute value aspects kicking in on this one. All right, so from these models, so we can see kind of like a level of importance going in. So I'm going to go back up. I want to take a look at this with the original. All right, let's rerun this because there's a point I wanted to make. All right, so what this has done, since we use the argument sort feature and we took the absolute values, we can see the magnitude that like room is going to be the most important in our model. And there's another way to extract it. We can use scikit-learn feature selection best. All right, so now let's take a look at how well does this do if I look at the predicted value versus the observed value. All right, so here is the true price, and here's the predicted price. If these don't match up well, then I know I've got problems in my model. All right, so I'm looking at this, and overall, these come together nicely, but you notice, hey, I see a pattern over here. So I can see that my model does not do well for the most expensive homes. So something that might be a wise thing to do is to actually exclude homes over 48 or so, and then build and rebuild this model, because this is going to be pulling down, this is definitely going to be pulling down the line in a manner that I really don't want it to. So it's a pretty good model except for the most expensive homes, but I want you to pay attention to something. I want you to see something very important with this. How good are the predictions? Like the quality, so like this point right here, that prediction right there, what is the vertical difference between the line and that? So if I was to make a prediction, well, actually, no, it's horizontal with how the author chose to do this. So if I have this point here, here is the predicted value. Their actual value is over here. You see that horizontal difference between the point and the line? If I have a point here, that was a predicted value, and over here is the actual value that corresponded to it. Here is a predicted value, and the actual value that corresponded is on the line horizontally to go in. So if I have this point here, and I go over, so this is maybe about, so about 20. Let's see, this is about 15. The actual value ended up being 20. And that's a good bit of money to have in between. So when we make predictions, we really, this isn't tight enough for me to be able to rely, put my job on the table for this. All right, so let's go ahead and keep working, keep looking at this. Here's the score. So that's with the regular linear model. Now that's also the training set. So that's going to be optimistic. And here, what we're doing is we're just looking at regression with one variable at a time. So if I wanted to see like how strong of a model could I have with just one predictor with each of them individually, this tells me how well like room would perform, or it gives me insight into how well room would perform by itself. Now I want to transform my data. All right, why do we transform our data? Okay, so when we start, I usually do this type of transformation when I'm trying to screen variables. So something that we can do, if I've got numeric variables, I've got different averages and for each column, and I've got different standard deviations for each column. All right, I've got different magnitudes of numbers. That means as I'm screening things, as I'm looking through, it's harder for me to interpret features such as coefficients. So it would make my life a little bit easier if a coefficient like directly corresponded to its significance. Now, if you think about the t-test, which we have it in the output for our regression models that we've already gone over. If I look at that, the t-value is really what tells me if it's significant or not. Well, it would be nice if I could have a more direct relationship between coefficients and t-value without having to do any mathematics in between. If I go through and I subtract the sample average and I divide by the sample standard deviation after subtracting, then I have mean 0, standard deviation 1. All right, so that makes it a little bit easier to interpret what's important. So from a prediction point of, or from a model point of view, the coefficient is more closely, like each of the coefficients is more closely tied to the t-value or the t-score, so I can interpret it easier. It's easier for me to look at the coefficients and pick and choose which one's the most important. If I don't do this rescaling aspect, I have to go through and manually check. So the transformations work better this way. Also, some models will use variables with greater standard deviation than others, believing that greater standard deviation means that it's a more, it's able to distinguish between values better. If I don't want to be susceptible to that, then rescaling deals with it. One of the things we have to remember about that is that in the future, when I go to make a prediction, I have to subtract off the original average, and I have to divide by the original standard deviation. If I don't do that, I'm going to have crap predictions for future stuff. And so here we're going to just rescale the x values. And so we just use a standard scaler to perform this from sklearn. And a lot of times, a lot of different model structures, such as neural networks, depending on how they were coded, will actually perform better with standardized data. And so I consider doing it. I almost always do it when I'm screening variables. It makes it easier when you standardize your data. You know that if it's positive, it's greater than the sample average, negative, less than the sample average. Makes it easier to kind of feel your way through the model building process. All right, so now let's just go ahead and do ordinary least squares. And let's go ahead and get our summary just to see how we feel about this. So we're using LSTAT. And we've looked at this stuff before. So this is just telling me it was the R squared. What's the adjusted R squared? You notice that these are pretty tight. That indicates I'm not overfitting. F statistic is big for showing that there is informative value inside this model. We can see that LSTAT is definitely statistically significant, and the coefficient is a little bit bigger than 1. Let's see, does anything jump out at me as something being problematic? No, no. All right, that's all I've got for you. I hope you're staying safe and enjoying, the class. Let me know if you need help.